Okay, in this lesson we're going to look at products and quotients of functions. So far you've seen how to combine functions through addition and subtraction. So now we'll see how to combine functions through multiplication and division. So to review, given f of x equals x squared plus x minus 6 and g of x equals x, write h of x, which is the product of the two functions, and then we'll look at k of x, which is the quotient of the two functions. So we'll start by subbing in f of x and g of x. So f of x would be x squared plus x plus 6, and g of x was just x. And if I simplify this, what I end up with is a cubic function. So I get x cubed plus x squared plus 6x. Okay, so the product of a quadratic and linear function ends up being a cubic function. For k of x, we're going to do division. So we'll look at f of x, which is x squared plus x minus 6, over g of x, which is equal to x. So now what you'll notice is that when you look at the quotient of a quadratic over a linear, you end up with a rational function. So it ends up changing the kind of function that we started with, and this one becomes a rational function. Okay, so what ends up happening here is because I now have a rational function, there may be some restrictions on the values of x that I can have. So earlier we had no restrictions on our values of x when you had a quadratic and a linear, but now that it's become a rational function, we know that we'll have some restrictions on the value of x because we can't have values of x that make the denominator equal to 0. Okay, so we talked about the superposition principle before. So just to remind you, the superposition principle is a convenient way to visualize the sum or difference of two or more functions. However, when two functions are combined through multiplication or division, the nature of the resulting combined function is less obvious. So it's a little bit harder to tell what kind of a function you'll end up with. Okay, so many of the skills you use to multiply and divide algebraic expressions will be applied in this lesson. Okay, so like I said earlier, we started off with a quadratic and a linear, and then it ended up being a cubic when you look at the product of them, or if you look at the quotient, it ends up being a rational. So it's a little bit harder to tell what the behavior of the function will look like when you are multiplying or dividing them. So the product and quotient of functions. So let f of x and g of x represent any two functions. Then we can define a new function h of x that is the product of f of x and g of x. So there's two different ways of writing it. So you'll either see it as the first function multiplied with the second function, or you'll see the first function multiplied with the second function and then the independent variable in the brackets on its own. So there's different notations of writing the product of functions. You can also define a new function which we'll call k of x. It doesn't really matter what variable you choose. This is just a convenient one to use. So we can also define a new function k of x that is the quotient of f of x and g of x. So we're looking at the division between the first function and the second function, or f over g of x, okay, which means the same thing. You're still dividing the two functions. Okay, when you are looking at the quotient, what ends up being created are some restrictions, and the restrictions are any value of x that makes g of x equal to 0. So you can't have g of x equal to 0, which is why now you have some new restrictions. Okay, so how do we combine these functions through multiplication and division? Well, we'll look at it in three different ways. We'll look at it graphically, algebraically, and numerically. So graphically, so if you have f of x and g of x in terms of a graph, what you would do is you'd find common x values, and you would take the y values that correspond to those common x values and multiply or divide them. Okay, so we'd multiply or divide the y values for the same x value, and then you can plot the new point. We'll also look at it in terms of how to do it using a table of values, just to help you organize your information. Combining functions algebraically, if the operation is multiplication, you multiply the functions. If the operation is division, you divide the functions. And then if there's any place that you can simplify, you simplify it as much as you possibly can. So this is similar to what we saw in the review part right at the beginning of the lesson. And then finally, if you're combining functions numerically, you want to multiply or divide the y values for the same x value and then state the new point. So it's very similar to combining functions graphically. You find a common x value, you multiply or divide the corresponding y values, and then you go with it from there. Okay, so in terms of the domain and range, when you are looking at the product of functions, so we're only going to specifically look at the product of functions. If you're looking at the domain of the product of functions is a domain common to the component functions. So in other words, it's defined only where the domains of f of x and g of x overlap. So depending on what the domain of f of x is and what the domain of g of x is, the domain of the product of the functions would end up being wherever those two domains overlap. Okay, so it's only defined wherever those two domains overlap. In terms of the range may vary based on the resulting function. So depending on what kind of function you end up with, you might get a new range. So restrictions on one or both of the original ranges may indicate the existence of or the absence of a restriction on the range of the resulting function. So really, the domain is the only thing that you can sort of look at and determine really easily. You just need to see where the domains of the original functions overlap. The range, on the other hand, it's a little bit harder to determine. You sort of have to look at the resulting function, and then you can set the range based on that. Okay. So, for example, here we have given a cubic function and a linear function. For these two functions, the range for both of them is all real numbers. However, if you multiply these two functions together and you look at the product of the cubic and the linear function, you end up with a quartic function. And if you think about what a quartic function looks like, it sort of looks like a parabola, a little bit wider at the bottom. And so you'll notice that the range is now restricted such that y is only greater than or equal to 0. Okay, so those are the kinds of things we mean by some restrictions on the range. So sometimes a change in the range occurs as a result of the product of the functions. Okay, in terms of the quotient of functions, this one's again a little bit harder to determine the domain and range. So the domain of the function, the domain of the quotient of functions is the domain common to the component function. So again, whatever domain you had for f of x and whatever domain you had for g of x, wherever those two domains overlap, that would be the domain of your quotient function. The only exception is that you can't have any values that make the denominator g of x equal to 0. Okay, so in addition to wherever the domains overlap, there may also be a restriction based on any values of x that would make the denominator equal to 0. Okay, in terms of the range, restrictions on the original range may indicate the existence of restrictions on the range of the resulting function. Again, much like the product, it's sometimes hard to tell what would end up happening to the range of the resulting quotient function. For example 1, it says use the graphs of f of x and g of x to graph the following. So here I have the product of f and g, so I'm multiplying f of x times g of x. So what you want to remember is that because I'm multiplying them and I'm given the graphs for each one of them, all I need to do is look for an x value and then look at the corresponding y values for each function and multiply them. So what you'll see here is that I've drawn a little table and I've already chosen some values of x, and these values of x that I chose are values of x that have nice corresponding values of y for f of x and g of x. Okay, so if I look at f of x, which is the quadratic function, so the blue function's f of x, at x equal to -3, it's equal to 0. At x equal to -2, it's equal to -4. At x equal to -1, it's equal to -6. At x equal to 0, it's equal to -6. X equal to 1, it's equal to -4. And then at x equal to 2, it's equal to 0. I didn't continue to 3 because it's kind of hard to tell what number it falls on. I think it falls on 6, but because I'm not 100% sure, I left it at 2. Okay, so I chose values of x that had nice values for f of x. Now I'm going to look at the corresponding g of x values. So when x is equal to -3, g of x is my red graph. At x equal to -3, it's also equal to -3. At x equal to -2, it's equal to -2, -1, and I'm going to just continue finding the corresponding y value on the red graph. And then I could have continued here. I can see that there's a lot of really nice points for my y values for g of x, except my values for f of x, there's not as many. So now, if I'm looking at the product of f of x and g of x, all I need to do is multiply my corresponding values. So 0 times -3 is 0, -4 times -2 is 8, -6 times -1 is 6, -6 times 0 is 0, and then -4 times 1 is -4, and then 0 times 2 is 0. Okay, so now if I plot those points, I have a point at -3, so now I'm going to look at my x coordinates and my y coordinates based on the product of the two functions. And so I have a point at -3 and 0, which is here. I have a point at -2 and 8, which is all the way up here. It's a little bit off the grid. -1 and 6, so -1 and 6. I have a point at 0 and 0, so right at the origin. And a point at 1 and -4, which is here. And then a point at 2 and 0, which is here. And if I sort of sketch this graph, I can see that it sort of comes down this way. This is a cubic function. Remember when we multiplied it in the review part? We saw that it was a cubic function. This part comes down here, passes through the x-axis, goes back up here, and it sort of does something like this. Okay, so you can sort of see that it's a cubic function, which is what we were expecting. Notice where all the zeros are, or where the x-intercepts are. You'll notice that it's either the blue graph or the red graph that already crosses that x-axis at those particular points. So the second point here, if you notice, it says the zeros of f and g result in the zeros for the new functions. And I wrote a little note here. If you're looking at the product of f and g and you're looking to see when that's equal to 0, either the first function had to equal 0 or the second function had to equal 0. And you can see that the blue graph was equal to 0 here, which is why our product function ended up being equal to 0 here. The red graph was equal to 0 here, and the blue graph was equal to 0 here. So that's why our resulting product of the functions ended up being equal to 0 at those points as well. There's another point here where it says if f of x is equal to plus or minus 1, then the product of the two functions is equal to plus or minus g of x. And I wrote a little note as to why that happens. So if you're looking at f of x times g of x, and f of x ends up equal to plus or minus 1, that means that this is going to be equal to plus or minus 1, and plus or minus 1 times g of x gives me plus or minus g of x. And you'll see that there is a point where actually g of x is equal to negative 1. And you'll notice that if I multiply negative 1 times negative 6, I get positive 6. So I get the same value but opposite sign there. And then here where it's equal to just 1, I multiply these two and then it gives me the exact same value. So if at any point in time one of your functions is equal to 1 or negative 1, the corresponding product function will have the y-coordinate equal to the other function's y-coordinate. I hope that made sense. Anyway, so same thing here. Similarly, if g of x is equal to plus or minus 1, then wherever g of x is equal to plus or minus 1, the resulting function would be equal to plus or minus f of x. And so it sort of looks like that. Okay, so if g of x is equal to plus or minus 1, the resulting function would be equal to plus or minus f of x.